What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 3, Review Exercises. Let's do it. Question number 1 for the following exercise, determine whether the relation is a function. So we're determining if it's a function as long as there is kind of like a unique x value. So for example, what would make it not be a function is if we had a repetition of one of these x values. For example, if I had a and then it was also going to a different value like f, okay? So if I had this duplicate x value, it would not be a function. But since this does not exist and all of these x values are unique, this would indeed be a function. Boom, done. For this question, it's asking whether or not this is a function. Again, x is our independent variable, which is usually the case in most of our x, y functions, relations, etc. And y is the dependent variable. Now, again, if we can get a duplicate, meaning if we get a value for x that gives us two different output values, y values in this case, then it would not be a function. And this is a giveaway, right? The fact that the dependent variable is squared, that's a giveaway that is probably not a function. But I'm going to show you an example. So let's say x is 13, right? So I can get to 13 in two different ways. For example, if y is equal to 3, right? 3 squared is 9 plus 4 is 13. But I can also get to 13 if y is negative 3. So the short answer is when you see the y value being squared, it's probably not a function because we can get these duplicate x values. But this is the proof right here is that, look, if I plug in 13 for x, I'm getting potentially two different output values, 3 and negative 3. So that means this is not a function. Boom, done. So for this question, we're evaluating these following 5 scenarios. So first, we're doing negative 3, meaning we're plugging negative 3 in for x. So check it out. So of course, negative 3 squared is 9 times negative 2 in front is negative 18. 3 times negative 3 is negative 9, or we could say minus 9, and this gives us a value of negative 27. Here we're plugging in 2. So again, I'm replacing every value of x with 2. 2 squared is 4 times negative 2 is negative 8. Plus 3 times 2, which is 6. Add those together, you get negative 2. Boom, done. Negative a, we're literally replacing the x with negative a. Negative a squared is just a squared. Negative a times 3 is negative 3a. That's it. Plug and chug. Boom, done. Now this one is plugging in regular a. So I'm literally just replacing all of my instances of x with a, and we get this. But then we're negating the entire function. So we throw a negative on the outside, which is kind of like distributing that negative, or negative 1 if you want to think about it like that. And then we get positive 2a squared minus 3a, boom, done. Last but not least, we're plugging in a plus h for x, which will look like this. Now, when we FOIL this, right, it's a binomial times itself. It's going to be a squared plus 2ah plus h squared. If you, again, you have to write it out. A plus h times a plus h. And then that's still going to be multiplied by negative 2. Over here, we're just distributing, boom, boom, and we get 3a plus 3h. We're not going to have any like terms here, so we're just going to go ahead and distribute and give that final polynomial, which will be negative 2a squared minus 4ah minus 2h squared plus 3a plus 3h. Here is the final answer for that last one. Boom, done. So for this question, we're trying to determine if this function is one-to-one, meaning there's no repetitions of x's, no repetitions of y's. So if I look at this, what is this? Negative 3x plus 5. That's a line, right? It's got a negative slope, a y-intercept of 5. But the main thing is there's no repetition. Repetition would occur if it curved up like this or it went like this, right? In this case, this wouldn't even be a function. It would fail the vertical line test. This would be a function, but it would fail the horizontal line test, which means it would not be one-to-one. But this is a line. It obviously is a function. It passes that horizontal line test, which means this is indeed one-to-one. Boom, done. So here we're using the vertical line test to determine if this is indeed a function. The vertical line test says at every point, if I draw a vertical line and I only hit 1 point, I don't hit 2 or more points of the function, then it is indeed a function. The vertical line test states that if I draw a vertical line at any point through this relation and I only hit 1 point on this graph, this is indeed a function. You can see at every point, we're only hitting it 1 time, not 2 times, not 3 times, etc. So by the vertical line test, this passes. Therefore, this is a function. Boom, done. So in this question, we're meant to use the vertical line test to see whether or not this relation is a function. And at every point I draw a vertical line. Notice I'm only hitting this graph once. I'm not hitting the relation in 2 or more points, which means this passes the vertical line test, which means this is indeed a function. Boom, done. So in this question, we're asked to graph the function. Now you'll notice that this is a quadratic, right? Because it's x squared. And it also got a -2, which is a shift down by 2. So if we remember our typical quadratic of x squared, we start at the origin. So since this has a vertical shift down by 2, we're going to start at 0, -2. So there's my vertex. I'm going to plot a couple other points around it. Let's just do 2 below and 2 above in terms of the x values. Now I'm going to plug in. If I plug in -1, I get -1 squared, which is 1, minus 2 is -1. Plug in -2. That squared is 4, minus 2 is 2, and we have the same values on this side as well. And that's what we want to see, nice symmetry around that line of symmetry for a quadratic function or a parabola. So we're going to plot these points, and then we will connect the dots like so, with arrows indicating this continues on forever in both of those directions. Boom, done. So for this question, we're meant to approximate f of -2, which means what is the function value when x equals -2? So here's -2 on the x-axis. Here's the function at -2. And what is that function value? What is f of -2? It looks to be +2. So 2 is the answer. Boom, done. For number 17, it says if the function value equals 1, then solve for x. So if we look up here, here's where the function value would be 1. Again, the function value is 1 when it's 1 on the y-axis. So we have 2 points here and here. So what is the x value at these 2 points? Again, I can't see exactly, but we're going to approximate. It's pretty close to 2, so I'm going to approximate as +1.8. Over here, it's symmetrical. It looks like across the y-axis, so we're going to say it's -1.8. So those are our two solutions. Boom, done. For this question, we're using the following function to find this value in simplest form. So when we say h of a, we're plugging in a for t. So it'd literally be -16a squared plus 80a. So I'm replacing every t with a. Then it's minus h of 1. So I'm plugging 1 in for t up here. So that'd be -16, right, times 1 squared is just 1. So -16 times 1 is -16, plus 80 times 1, which is 80. But again, we're minusing. So this minus is actually going to distribute to the 80 over here. So I'm going to keep that in parentheses, right? And then this is over a minus 1. Okay, now we can simplify. So -16 plus 18 is 64. And then we distribute that negative. Check it out. So then we say minus 64 over a minus 1. Now we can simplify a little bit on top. We can see if this is factorable. Now, first of all, there's a GCF on top of -16. So check this out. If I pull out a -16, I'm left with a squared minus 5a plus 4, right? Because if I redistribute it, I get -16a squared, boom, +80, and -64. And all of this is still over a minus 1. Now I'm going to see if I can factor the numerator, which I can. So what two numbers multiply to +4 add to -5? That is -1 and -4. And look at this. We can cancel. And this leaves us with a final answer of -16 times a minus 4, where we distribute, we get -16a plus -4 times -16, which is 64 for the win. Boom, done. For question number 21, we're asked to find the domain. And when we're talking about domain, what we're really talking about is what are values of x that cannot be possible for this function. So really, in this case, since it's a rational function, we're looking at places where values of x are going to give us 0, because we can't divide by 0. We can't have 0 in the denominator. So the first step is we're going to factor the denominator. So of course, x minus 3 stays as is. And then for the denominator, we ask the question, what two numbers multiply to -12 and add to -4? That would be -6 and +2. So now that we have this factored correctly, we can see that there are two values of x that are going to make this denominator go to 0. The first is going to be 6. The second is going to be -2, right? -2 plus 2 is 0. 6 minus 6 is 0. But these are actually values that cannot be for x, which x cannot equal. What that means is our domain is everything but 6 and -2. So if we're putting this in interval notation, we're saying everything starting from -infinity all the way up to -2, but not including it. Hence, we have the curved parenthesis as opposed to a bracket. Then we pick right back up on the other side of -2 and go to 6. Again, we're not including 6. 6 is not allowed. And then we union that, and then we go from 6 all the way to positive infinity. So basically, this interval notation means any value other than -2 and 6 will be acceptable in the domain. Boom, done. So when we graph a piecewise function, basically in this case, we've got two different functions that we're graphing, and they each live in two different universes. So for example, the top one, x plus 1, lives in the universe where x is less than -2. So strategy that I like with this is I'm going to start right at that dividing point, right when x equals -2. What is the value of this top function? Well, I'm going to plug -2 in for x and get that function value. So -2 plus 1 is -1. So that means I can start at a coordinate of -2, comma, -1. So we're going to do it right here, -2, -1, and an open circle. So the reason why I'm having an open circle here is because this says when x is less than -2, not less than or equal to -2. So that value doesn't truly exist, but it's a nice starting point. Then all I need, since this is a line, is one more point to the left, because again, this is when x is less than -2. How about -3? Let's plug and chug. So -3 goes in, and we get -3 plus 1, which is -2. There's another point. So -3, -2, like so. Now all I'm going to do is I'm going to connect the dots like so. And this looks like a nice linear equation with a slope of 1. And that makes sense with what we see here, x plus 1. That's a slope of 1 in front of the x, y-intercept of positive 1. But anyway, it stops at -2. Now what about this second part? So again, I'm going to start off by plugging in a value right at that starting point at -2. So if I plug -2 into the bottom function, -2 times -2 is 4 minus 3 is 1. So here we have -2, 1, and I'm going to make that a nice solid point because again, this is x is greater than or equal to -2. Then I'm going to get one more point. I could plug in -1, I could plug in 0, I could plug in 1. I'm going to plug in 0 just because it's easy, and I know this is going to work because this is a nice linear function. So 2 points, we connect the dots, we're good to go. Plug in 0, that becomes 0 minus 3, which is -3. There's our second point, 0, -3, like so. Now we're going to connect those dots, and boom, there it is. So here is our nice graph of the piecewise function. Boom, done. For this question, we're meant to find the average rate of change from 1 to 2. So all we're doing is we're getting those two coordinates when x equals 1, x equals 2, and then we're taking the slope. That's what average rate of change is. So when I plug 1 into this equation, I get 10 times 1 squared, which is 10, plus 1 is 11. And when I plug 2 in, I get 2 squared, which is 4 times 10, which is 40, plus 2 is 42. Now I can calculate the slope, and I'm going to use my nice slope formula for two coordinates. So I do y1 minus y2, and again, I'm kind of just subtracting down if that's easier to think about. And then I do over the difference of the x's, which is 1 minus 2. Notice how I'm keeping that same order. This gives me -31 on top, -1 on the bottom, which gives me a slope or average rate of change of positive 31. Boom, done. So for this one, we're trying to figure out where the function is increasing and or decreasing. So what does it mean when it's increasing? It means it has a positive slope. So I can see that I have a nice vertex right here at 2, -2. This is when the slope is going to change over from negative to positive. So leading up to that vertex, it's going to be decreasing. That's everywhere from -infinity up to 2, but not including 2. The slope is actually 0 right there. It's not increasing nor decreasing right at that one point. So we're not going to include 2. And then increasing, aka positive slope, right, going from 2 out to infinity like that. So we're going to say increasing from 2 to infinity. Boom, done. For this question, once again, we're asked to figure out where the function is constant, increasing, or decreasing. So when we talk about increasing, it's where the slope is positive. And my slope is positive right from this point, which is at -3, all the way up to this point, which ends at +1 for the x values. There is no place where this function is decreasing because there's no negative slope. The only other two regions are from here and here. Both of those have a nice slope of 0, which is a constant slope. So it has a constant slope of 0 from -infinity all the way up to -3, not including unioned or joined with from +1 out to infinity. Boom, done. So for this one, when we're talking about local extrema, we're talking about a local min and a local max. So what is a local min? What is a local max? So the way I like to explain both of these is a min is like the bottom of a valley, okay? It's literally the low point. And we have a bottom of a valley occurring right here. A local max is the top of the hill. It's right here, right? So that's how to identify it visually. Now let's put in the coordinates. So my local minimum looks like it's occurring at -2, -3, like so. And my local max is occurring at +1, 3, like so. Boom, done. So for number 33, we're asked to find the absolute maximum of the function graph below. So an absolute max is the absolute max. It's literally what it says. It's the highest point that you can find on this graph in total. Well, there's a slight issue with this question, which is this arrow going up. And that means it's going to go up indefinitely, meaning there's not really an absolute max. It kind of goes on and on forever up to and approaching infinity. But there is a local maximum. And if we think about it in terms of what is displayed on the graph, if we assume that we're not looking at anything else, we could say that this top of the hill is the absolute maximum. Again, that's if we put off to the side the fact that there is this arrow. So what is the location of this maximum right here? We're going to approximate and say it's roughly not exactly at -2, but close to it. Let's say -1.8, and that's a height or function value of 10. So there'd be your coordinate of the max. Boom, done. For this one, we're first meant to find f of g of x, and then we're meant to find g of f of x. I'm going to use slightly different notation because I think it makes a little bit more sense in terms of how to approach these. So check it out. I like this notation better, even though it's equivalent, because it shows me that what I'm doing is I'm taking g of x and I'm literally plugging it into f of x. So what we're doing is we're replacing every instance of x with g of x. So here I have an x. I'm going to replace that, just leave that open. But there is my full f of x function. And then in place of the x, I'm going to put in the g of x, 5 minus 6x. Then we're going to distribute and simplify. I got 15 minus 18x plus 2. Now we can combine the 15 and the 2, which makes it negative 18x plus 17. Boom, done. Now what about g of f of x? So same thing. I'm going to write my g of x function, the big function, with a parentheses where the x is, because now I'm taking my f of x and I'm plugging that into the function, replacing every instance of x. So now I have this times 3x plus 2. We're going to distribute. Don't forget to bring that negative along with it. So it's 5 minus 18x minus 12. Combine the 5 and the negative 12. We have negative 18x minus 7. Boom, done for both of these. And there it is. So once again, for this question, I'm going to rewrite these in a slightly different notation that still has an equivalent meaning. So here is f of g of x. And so I'm going to start by writing out f of x, but I'm going to put a parentheses as a placeholder for the x, because what I'm doing is I'm plugging in g of x into every instance of x for f of x, okay? So then that just gets replaced with 1 over x. And now we can simplify if possible, but this is pretty much good to go. There's not really a whole lot we can do or simplify. So I'm going to leave it just without the parentheses as radical 1 over x plus 2. Boom, done. For g of f of x, we're going to do the opposite. It's 1 over, that's g of x, 1 over x. I'm going to leave that as a placeholder. And then I'm going to add in f of x, which is radical x plus 2. Once again, there's really not much to simplify. I'll just rewrite it without the parentheses. 1 over square root of x plus 2. Boom, done. So here we're finding f of g of x, and then we're going to find the domain. So first, let's do that. Now again, we're going to start with parentheses as placeholders wherever x is for f of x, like so. And then I'm going to plug in 1 over x into each of those instances, because that's what g of x is. We got 1 over x and 1 over x. Now all we're going to do is we're going to simplify this just a little bit to get rid of this fraction in a fraction. I can do that pretty easily and pretty nicely by multiplying by x over x. This is pretty cool, because this is going to multiply that, and this is going to multiply this and this. And you're going to see how it's going to eliminate that fraction on top of a fraction. So x times 1 over x is just 1. X times 1 is just x over x times 1 over x is again just 1. X times 4 is 4x. So now we have this nice final function. Now when we're talking about the domain, we want to look for values that are restricted, right? So once again, anything that's going to make this denominator go to 0 is out. And what's going to make that denominator go to 0 is negative 1/4, right? 1 plus negative 1/4 times 4, that's 1 plus negative 1 is 0. So x cannot equal negative 1/4. And then we also have to go back to this original piece before we simplified it, because these are little fractions in and of themselves, meaning I can't be having 1 divided by 0 in either of these cases. So 0 is also out of bounds. So those are the two domain restrictions. And just for fun, if I wanted to put this in interval notation, we'd say everything from negative infinity up to, but not including negative 1/4, unioned with everything from negative 1/4 up to, but not including 0, unioned with everything from 0 to infinity. Boom, done. So once again, I'm going to start out with f of x, but I'm going to put a nice parentheses where the x is, because we're plugging g of x into x here. And then it's 1 over the square root of x. And now we're just going to rewrite it without that parentheses, 1 over radical x. So the question now is, what is restricted? So we have two things we have to consider now, because we have a square root and we have a rational function. So first is the denominator cannot equal 0. That we already know, because it's in the denominator, can't divide by 0, fine. But because it's a radical, we also have to have a restriction on taking the square root of a negative, because that would put it outside of real numbers. So x also has to be greater than 0 as well. And I normally say greater than or equal to 0. We can take a square root of 0, that's fine. But because of this restriction, we can't include 0. So basically, x has to be a positive number. So this encapsulates that. So we'll just say x is all numbers greater than 0. That would be the domain. And if we did that in interval notation, it would be simply 0 to infinity. There you have it. Boom, done. So for this function, we're trying to find two functions that if you take the composition of said two functions, we're going to end up with h of x. And the composition is going to be f of g of x. Okay, so because this entire thing is under a radical, and by the way, there's multiple ways to do this, but I think this is the easiest way. Because the entire thing is under a radical, I can just make the main function, or the big function, f of x as square root of x. That means whatever g of x is, f of g of x will put the entire g of x under a radical. Well, since this function in here, or this fraction in here under the radical is 2x minus 1 over 3x plus 4, it makes sense for that entire fraction to be g of x. Then f of g of x is the square root of g of x, aka the square root of this, which is h of x. Boom, done. So graphing a function like this that is a transformation can be done pretty easily if you know what the baseline function x squared looks like. So normally it kind of goes up like this, like a nice parabola. This is just approximation, obviously. And what's happening? This is x minus 3. You're minusing 3 from the x. That's a rightward shift by 3 units. So the new vertex, instead of being at the origin, is going to be here, and then you're going to have your typical parabola. But I'm going to also show you how to graph this using a quick table, just might give you a little bit more context. So since we know that nice vertex value is occurring at 3, 0, again, basically where this part zeroes out, that's a nice shortcut in terms of finding the vertex. When you have a function looking like this, you want to zero out whatever's in that parentheses with x. So we know that vertex is there. I can try 2 more values right around it. I can try 4 and 5, and also another 2 going down, 2 and 1. So now when we plug in 4, we get 1 squared, which is 1. Same with 2, we get negative 1 squared, which is also 1. Plug in 1, we get negative 2 squared, which is 4. And plug in 5, we get positive 2 squared, which is also 4. So now we have 3, 0, 4, 1, 2, 1, and 5, 4. 1, 4, excuse me, and then we get this nice looking parabola. Boom, and notice that nice symmetry along the vertex, along the line x equals 3. That's how you do it. Boom, done. So for this function, once again, if you're familiar with the radical function, which kind of looks like this, we can see that this is an addition to the function itself, which is a vertical transformation up by 5. So I do know that I could take this, transform it, and I'm pretty close to the mark. But once again, we're going to plot it out nicely with a couple coordinates just to give you a little bit more context. I really like doing this to make sure the graph's accurate. And again, start with that central point. It's kind of like the vertex here. It's just going to look a little bit different than a quadratic, but where you're going to zero out what's under that radical. So that's, of course, when x equals 0. So we know we have a nice value at 0, and you plug it in, you get 0 plus 5, which is 5. Now, the thing is this is going to progress to the right, because we can't take square roots of negatives anyway. So that's a nice starting point at 0. Now I'm going to try 1. And the second point I'm going to plug in is not going to be 2. It's actually going to be 4. The reason why is because I want to make it easy on myself. I want to pick values that are Nice and easy to take the square root of. So square root of 1 is 1 plus 5 is 6. Square root of 4 is 2 plus 5 is 7. So we got 3 points. We got 0, 5. We've got 1, 6, just like we predicted, and 4, 7, like so. And then we get this nice graph. Boom, done. So again, knowing the baseline function here is helpful. Typically, cube root of x looks something like this, okay? Something like that. And the thing is we have a negative inside. So when you apply a negative to the x value inside, what that does is that reflects this across the y-axis. So we can say roughly, right off the bat, we know roughly this is going to look something like this. But again, we're going to use that strategy where we're going to make a table, and starting at that value, that's going to zero out what's inside the radical, which is again going to be 0. So that's nice. A nice starting point at 0, 0, which is the origin, which is what we predicted. Then I'm going to choose a value to the right and to the left, which would be -1 and 1. And then I'm going to carefully pick my next value. Again, I'm not going to do 2 or 3 or 4. I want to choose values that are nice, perfect cubes, so I can make this as easy as possible on myself. So the next one would be -8 and +8. So check this out. If I plug in -1, that's going to become +1. The cube root of +1 is 1. And then over here, if I plug in 1, that's going to be -1. Cube root of -1 is -1. Likewise, when I plug in -8, that's going to be negated. So it's +8. Cube root of +8 is 2, because 2 times 2 times 2 is 8. Boom. And then I put in that +8 with the negative in front of it. That's -8. Cube root of -8 is -2, because -2 times -2 times -2 is again -8. So now we got some nice points here. -1 is 1. +1 is -1. -8 is 2. +8 is -2, so that lines up with what we predicted just based on the transformation, and then we'll connect the dots as best as we can, putting nice little arrows out there. And there's your graph. Boom, done. Here we've got a nice absolute value function with a few different transformations happening, okay? So the first thing is we're shifting it 2 to the right, then we're stretching it by 4 outside here because it's multiplying this entire function, and then we're shifting down by -6. But the thing is, because 4 is multiplying that -6 as well, it's actually going to shift down by 24. So for this absolute value function, we actually have 3 transformations happening. We're going 2 to the right, then we're going to have a stretch of 4. That's a vertical stretch when you're multiplying the entire function. Last but not least, we have this -6. So you might say, oh, that's a vertical shift down by 6. But it's all being multiplied by 4. So in actuality, it's a vertical shift down by -24. So I could rewrite this as follows. 4 times the absolute value of x minus 2 minus 24. So you already have a rough idea of the transformations being applied. But I'm going to use that similar strategy where we're going to make a table so you can see the points a little bit more concretely. And once again, I love this idea of starting at the vertex where you're going to zero out, in this case, whatever is inside the absolute value. So that's going to be at +2. When I plug that in, I get 0 times 4, which is 0, minus 24 is -24. Now for my other points to plug in, just to give this a nice fleshed out appearance, I'm going to also try 1 and 0, and I'm going to also try 3 and 4. So when I plug in 1, I get 1 minus 2, which is -1. Absolute value of that is 1 times 4 is 4, minus 24 is -20, okay? And that's going to be the value for 3 and 1 because an absolute value function has that nice property of symmetry, just like a quadratic. Then I'm going to plug in 0. 0 minus 2 is -2. Absolute value of that is +2 times 4 is 8. 8 minus 24 is -16, and we'll get the same value with 4 as well. So now we got some nice points. Let's plot them out. So we got 2, -24, which is occurring right here. We've got 1, -20, as well as 3, -20. And then we've got 0, -16, and 4, -16, like so. Now, as we connect the dots, we get that classic V shape that we're used to with absolute value functions. There it is. Boom, done. So for this graph, we're meant to show f of x minus 1 if this right here is f of x. So what's the transformation in question? That's the real dilemma here. And when you subtract 1 or add 1 to the x directly, that's a horizontal transformation. Adding 1 would be moving it to the left by 1. Subtracting 1 is moving it to the right by 1. So what I can do to graph this transformation is I can take each point and shift it 1 to the right. This one will go 1 to the right, and this point will go 1 to the right. So we're still going to have this nice semicircle shape. I'm going to do my best here to graph it, but it's going to look something like this. There's your transformation. Boom, done. So for this one, we're meant to write the equation of the standard function represented by this graph. So I see that it's a v, so it must be an absolute value function. And we also can see that the slope is 1 going to the right, -1 going to the left. That means there's no vertical stretch being applied here. And really the only transformation I'm seeing is it's shifted 1, 2, 3 to the right. That's where the vertex is. So I'm going to have my typical absolute value function of x. The only thing is I'm going to have a -3 inside the absolute value. If it was outside, it would be a vertical transformation. So inside, horizontal, -3 to showcase the 3 units to the right. There it is, done. So to determine whether this is even or odd, what we need to do is we need to plug in -x into the function and see what happens. So when I plug in -x, I've got -x to the 4th power. And what is -x? Times itself, right? Those 4 times, -x times -x times -x times -x. It just becomes regular x to the 4th because a negative times itself in even number of times just goes back to positive, right? So it ends up being the exact same function as what we started off with. When that happens, that means that the function is an even function. Boom, done. Once again, we're trying to figure out if this is even or odd, so that requires a test where we plug in -x into the function. So I'm replacing each x with a -x, like so. Now we have to look at this and kind of simplify a little bit, and that becomes -1 over x minus 3x. And what has happened is the function does not return back to its original state, which means it's not even. But what has happened is we've got a new function that is basically everything has been negated. Everything is now the opposite of what it once was. That fits the criteria for an odd function. And just to let you know, even if one of these terms was not flipped, then it would be neither. Okay, so in order for it to be odd, everything has to be flipped. Boom, done. For this question, we're determining whether or not it is even, odd, or neither. So I can right off the bat tell you that this is not odd because odd requires symmetry about the origin, which this is not symmetric about the origin. For an even function, it must be symmetric about the y-axis, which it absolutely looks symmetric across the y-axis, right? We have this nice U where we can map every point to the left of the y-axis with a point on the right of the y-axis. So this, of course, is an even function. Boom, done. So for this question, a few things have happened, right? We can see that the slope is no longer 1 and -1 to the right and to the left. It looks like 1 over 2 and -1 over 2, like so. Also, you can see that the vertex has been shifted 2 to the left and 1 up. So let's put that all into our function. So first, we've got that vertical compression by a factor of 1/2, right? Because the slope was 1, now it's 1/2. So that goes outside the absolute value bars. Then we've shifted our vertex 2 to the left. That means we would say x plus 2, right? Plus 2 inside goes to the left, -2 would go to the right. Last but not least, we shifted it up by 1. That's a vertical shift up by 1, so we put a +1 out here. And here's your final function. Boom, done. So for this one, a few things have happened. Number one, it's going down, right? That's a reflection across the x-axis, so that means we're negating the function. The other thing that's happened is that the slope is no longer 1 and -1. It looks like 3, right? Down 3 and over 1, that's -3. Down 3 into the left one, that's +3. So we're going to need that vertical stretch of 3. And then the vertex has been shifted to the right by 3 and up by 3. So let's put all that together. So out in front of the absolute value, I'm going to have the negation and the 3, right? So I'm both flipping it across the x-axis and I'm stretching it by 3. And then to signify the vertex, since the vertex is at +3, that's a shift to the right. Again, we -3 to go 3 to the right. And then going up 3 vertically, that's a +3 outside of the absolute value symbols. So here's our final function. Boom, done. So for this function, we can see 2 transformations happening. The first is it's shifted 3 to the right. The second is it's flipped across the x-axis. So normally we'd have a vertex here. Now it's going to be here, 3 to the right. Normally this would go up like so, but now because of that negative in front, it's going to be flipped down like so. But just to give you a little more context, we're going to once again do that nice XY table just to get a few concrete values. So my vertex is going to be that starting point where we're going to zero out the absolute value, which is going to require a 3. Plug in 3, we get 0. Then I'm going to test 2 other points. How about 2, 1, and 4, and 5. So here when I plug in 4, I get 4 minus 3, which is 1. Absolute value of 1 is 1 times negative is negative 1. Same with 2. 2 minus 3 is negative 1. Absolute value, that's positive 1. Negated is negative 1. With a 5, we get 5 minus 3 is 2. Absolute value is 2. Negative 2, and we get a negative 2 up here as well. So the other points would be 2, negative 1, 4, negative 1, 1, negative 2, 5, negative 2. And then we're going to connect the dots like so. Boom, and boom. There's my nice absolute value. Boom, done. So for this function, we're meant to find the inverse. And the way I always like to start by finding an inverse is I swap this out for y equals 9 plus 10x. After that, I switch the x and the y. So I say x equals 9 plus 10y. Then I isolate the y. So I'm going to subtract by 9 first, and then I'm going to divide by 10, just straight variable isolation. And I get y equals x minus 9 over 10. But this is our inverse function. So the last step is just put it in that nice inverse notation. So I'm replacing y with f inverse of x equals x minus 9 over 10. Boom, done. So first of all, we know that this is a parabola, right? We know that it's going up, something like this, and we know it's going to have a vertex here. Now, if we want that domain where it is one-to-one and non-increasing, well, it's got to pass that horizontal line test. So obviously, as is, it does not. But if we start at that vertex value and follow it to the right, that's going to be increasing, and it's going to be one-to-one. So we can restrict the domain as follows. And by the way, where is the vertex occurring, right? It's occurring at negative b over 2a. Well, b is 0, so we already know the vertex is occurring at 0 for the x value. It happens to be 1 for the y value. You can figure that out by plugging in 0 for x. That domain where we're restricting it by is going to be everything from 0 to infinity. So that's the domain. Now let's calculate our inverse function. So again, we're going to start by saying y equals x squared plus 1. Then we're going to swap the x and the y. We're going to say x equals y squared plus 1. Then we're going to isolate y. So first we're going to subtract by 1, that equals y squared. Then we're going to take the square root, and we're going to get y equals the square root of x minus 1. Last but not least, we put in that nice function notation. F inverse of x is equal to radical x minus 1. Now, when it comes to restricting the domain of this function so that it works with our restricted domain here, we're actually not applying the domain, we're applying the range to this restricted function. And the range of the original function is going to be the domain of the inverse and vice versa. So since we got this domain here, well, what would that range be? So the range is going to be everything starting from this point going up, so from 1 to infinity. And that's what we impose as the domain for the inverse. It's everything from 1 to infinity. And this makes a lot of sense because think about it. What you're doing is you're cutting off the values where you're going to be taking the square root of a negative, right? When you plug in 1, you get 0. Anything above that, you get a positive. So that makes perfect sense. There's your function. There's the accompanying domain. Boom, done. So for this question, what I did is I used Desmos to generate a nice graph of the function 1 over x. There are arrows here and here, but that's just for fun to add on so you can see that it goes on and on forever. Now, is this one-to-one? Well, to answer that question, does this function pass the horizontal line test at each and every point? And the horizontal line test is whether or not it hits 2 or more points with a single horizontal line anywhere. Well, since it never does, it passes the horizontal line test. Every place where you can draw a horizontal line, it only hits the function once. Then I would say, yes, this is indeed one-to-one. Boom, done. So for this question, it's starting off by saying f of 5 equals 2, which means that if you plug in 5 as an x value for this function, you're going to get 2 as an output. Now, the most important thing to remember about inverses and the functions from which they stem from, they have inverted value inputs. What that means is whatever I plug in for x to get a corresponding y value for my original function, it will have the same relationship but flipped, meaning when I plug in this value here as the x value for the inverse, I get the same x value for the original function as an output for the inverse, okay? So that's a fancy way of saying that whatever coordinate you have for the original function, the inverse of that, or the flipped around values, will exist for the inverse. So I could also say, for example, let's just make this up. If I had 1 comma 7 as a point for the original function, I'd have 7 comma 1, which is a nice way to answer this question because they're saying, what is f inverse of 2? Well, since I know that 2, 5 exists for the inverse function, then I know that the output of f inverse of 2 would therefore be 5. Boom, done. I hope you guys enjoyed this video, and if you did, please click that like button. If you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.